So a little bit about me. I'm a PhD, but not in data sciences, in computer engineering. Yes, I'm not a CS major, and now it's on tape. But the thing is, I've been doing this for 20 plus years. I've been doing software development as a student, as a researcher, as a manager, as a community manager. And the one thing I can tell you, right, the one known is that tech changes, right? The only thing certain is change. I'm also an innovator. I'm a community manager. I run Google Developer Group in New York City, Google Developer Group in Hudson Valley. We're doing a DevFest in 3 weeks. I don't know why I'm here, but if you're in New York City, please come see us. I'm also a mom. And the reason I say this is it'll become clear to you later why I think this is important. The two things I'm passionate about are inclusiveness in communities and workforce retraining. Hopefully, I'll connect the dots later. So we have to have some goals for every talk, right? So the goals for this talk are really simple. If you are a beginner, I would have done my job if at the end of this, you're walking away saying, hey, I can answer this question. What's machine learning and why should I care? If you're a developer, you should be able to answer the question, how can I use machine learning to solve my problems? If you are a human being, you should be able to say, why do these challenges in machine learning and AI matter? If you're not a human being, I don't know what you're doing here. There is no fourth category. So let's get started. As a beginner, what is machine learning? So I'm going to take 1 second to have someone shout out what they think machine learning is. Takers, don't make me point. Oh my God. Oh, fine, fine. Yay, OK. So there was a scientist in the room because he kind of said this. So scientists, when you talk to them, will say machine learning is about turning data into information, right? And the idea here is that you've got so much data going on in the world that it's beyond our human cognition to be able to process multidimensional data. Machines will be better at it. And so when a scientist says, hey, it turns data into information, it means you can take huge amounts of data and pick up meaningful insights from it. That's the scientific definition. You talk to a developer, they don't care how that happened. To them, machine learning is about turning data or using that data to answer questions. Can I get something out of it that makes my job easier, right? So from that perspective, machine learning is really like if you see this and say, hey, what is this? Your machine should tell you that's a fish. Or if you say, I'm playing chess, what's my next move? It should say, if you do this, you will win the game, right? That's what they expect, actionable stuff. But if you're like me, and you're a parent, I want you to think about this as another way to think about machine learning, right? Machine learning is exactly like teaching your toddler stuff, right? We've all done it. So what does that mean? And it'll give you a different lens to think about it. It means this is what I do with my 3-year-old. When he was 3, he no longer is. But this is how it would be. I would teach him a concept using examples. So I want to say, hey, remember those picture books? This is an apple. That is an orange. Then you'd validate that learning. You'd say, hey, I'm going to show you a picture now. What is this? And he should say, that's an apple. And you should point an orange and say, is this an apple? And he should say, no. Then you know he learned it. My son, however, I would point a ball, and he said, that's an apple. And I said, sure it is, because technically it looked like one. But that's what that is, right? That's the validation. The real value comes when that child or computer has gained enough expertise that they can then that you can assign tasks to them that they can fulfill based on that knowledge. This is when I could then go to my 3-year-old and say, now you know what an apple is, pack your own apple for lunch. There's the bowl, pick the fruit, right? That's exactly what it is. But that's machine learning. What's deep learning? Let's take this analogy a little bit further. Machine learning is teaching simple concepts. Deep learning is the ability to see patterns, right? Relationships that you couldn't see just at the surface. So I'm going to try this analogy again. This might break down, but let's go with it. Here's my son again, featured. So I teach him a concept. This is bread. This is jam. This is a cookie. That's a concept. Then I say, let me make you a sandwich. Put jam on it, stick 2 bread slices together. That's a sandwich. But he's looked at this pattern, and he says, aha, what did you just do? You used jam as glue. So he learned 2 concepts. A, this combination of stuff is a new thing. And B, jam, glue stuff together. And he did this. He came back and said, look, mom, cookie sandwich. I put jam and stuck them together. And I was like, yes, transfer of learning, right? He took a concept he learned in one domain. He applied it to another. And that was the value of the learning. So that's deep learning, right? OK, we can stop talking about my son and talk about the world. Where is deep learning being used? So it turns out we're already seeing it everywhere. In fact, if you think about machine learning in industry today, you're probably talking about deep learning. So here is, I think this is Pinterest, yeah. Pinterest Lens, right? You can take pictures with it. It tells you what's in there and takes you to a place where you can buy stuff. So you're using it for discovery. You can use it for diagnostics. This is IBM's Watson, right? They use computers to basically detect cancers and determine if a tumor is malignant. And the interesting thing is they said, we already show that it's better, it's more accurate than a pathologist, which kind of is another lens to look at it, right? Can a machine do the job of a human better than the human can? There's anomaly detection. This is in the financial markets, right? They're like fraud detection. Can I use computers and machine learning to detect patterns of fraudulent behavior and save money? Again, one of the reasons they're doing it is they're saying it's really productive. And then there's entertainment. How many of you here use Snapchat? You can admit it. I don't, but yeah. OK, so filters, right? All the filters, all the fake stuff you put on these pictures, right? Again, machine learning at play, but this is really about entertainment. There doesn't seem any significant value, but still something had to learn that when you put ears on a face, it better go over the ears and not over the eyes, right? So that kind of gives you a gut sense of, OK, machine learning is about teaching something by example, having it learn a concept, and then applying it to do other stuff, right? But you're a beginner. Why does it matter? So this is kind of the bad news. There's this article that says how to secure your job in the age of automation. But the bottom line, and the thing that I liked about this, is that they highlighted the fact that machine learning is making it possible to automate jobs that were normally not considered automatable, right? If that's a word. Meaning, previously it was mechanical stuff you'd automate. Now you can automate knowledge work. Knowledge work that was typically the domain of humans is now fair game for machines, which means all of us need to kind of be working with this, right? Trends reflect this awareness. This is Google Trends. And I'm going to ask you again, come on, crowd participation, a little bit, please. What do you think happened in 2015? That's OK, you saved me a minute. So I'll actually say something here. If you look at it, it was 25, the word machine learning, the trend, was at 25 before. In 2015, something happened, and it's been at 100 ever since it started ramping up. Why? 2015 was the year, and I'm not crediting Sundar Pichai with everything, but I'm just saying that in 2015 at Google I/O, he said, we are going away from mobile first to AI first. We're going to double down on machine learning and artificial intelligence. But you can't give him all the credit. I really like this. You can't see all of this, but this is literally a newsletter from machine learning, things that happened in 2015. If you kind of zoom in, and I'll send you the slides later, everything happened. Facebook open source Torch, 2015. Amazon started machine learning platform, 2015. If you look over there, Microsoft officially launches their Azure machine learning platform, right? Tons of stuff were coming out on a daily basis in 2015. What does that mean? This is how I kind of look at the space. What it meant is we were at this perfect confluence of four factors, right? One, the world was getting filled with a ton of data. IoT was generating data, weblogs were generating data, mobile phones and devices, wearables were generating analytics data. So much data, we were swimming in it, and we didn't know how to manage it ourselves, right? That was one. Second, the cloud took off, right? Now, a lot of the things that we would do on our little desktops, you could scale processing in the cloud. That means that you've commoditized the two big parts of machine learning that were from the technology perspective. And then from the people perspective, we saw huge amounts of open source stuff come out, right? Open source because the big companies, the ones who own the data, recognize the fact that they're never going to get further if they don't allow more eyes on this problem. And so the open source meant that people who normally didn't have the research capabilities could start from a further point and move forward. And finally, I cannot state this enough, developer advocacy, right? People going out talking actively about it, saying, hey, you can do this. It's not for PhDs anymore. And this was actually one of the big messages that you hear often. This is Fei-Fei Li, who was talking about democratization as really reducing the barriers to accessibility of these technologies. That means making it easier for anyone else to use it. But what does that mean, right? As a developer, how do I use this to solve problems? And I'm specifically thinking about developers, not data scientists. So if you know data science, this may not be relevant. But as a developer, this is why I kind of say pragmatic machine learning, right? What does pragmatic mean? Pragmatic means you want to deal with things sensibly and realistically, right? Think practical considerations, not theoretical ones. And I'll break it down really simply and say sensible means ask yourself, is machine learning really what I want to do to solve this problem? Don't be like drinking the Kool-Aid, right? Don't be like, I'm going to apply machine learning for everything. I have this tiny app that I'm going to do machine learning for. No. Don't waste your time. Scope it. Second, once you've got past that and say, yep, I do need to use machine learning for this problem, you want to ask yourself, realistically, how do I get there knowing that I don't know anything about it? And because of that, we're going to talk about this model of like leverage, adapt, and make. And please appreciate the little basketball. My son was actually in a basketball game today that I'm missing because of this. But also, I kind of, this is geeky, but I made this into an acronym that says SLAM. So that's supposed to be a slam dunk. It won't happen again. This is my one corny joke, OK? Deal with it. But really, what I want you to think about is the path to machine learning is 4 things, right? You start, most of us are going to be at the bottom, right? Everyone is going to be there. Very few people are going to get to the top. When you're at the bottom, you're in the scope mode. You're like, do I even need machine learning? Then you go to leverage, adapt, and finally to make. And we're going to walk through this. At a high level, you want to look at this as a split after the red part. At scope, sometimes you'll say, hey, machine learning is not for me right now, and just exit. If you stick with it, then what you really want to think is it's an evolutionary process. Don't try to like go from doing nothing to being the head of Facebook engineering overnight. It's not going to happen, right? So that's pragmatic. So we're going to try to break this down and look at this. First is machine learning the right solution for this task? So the way you want to think about it is that traditional programming. If you have a problem you want to solve, you can solve it in 2 ways. One, traditional programming, where you tell the machine what to do, step by step, you hold its hand. Or machine learning, where you give it examples and say, you figure it out. Which one do you take, right? That's the thing. So the first question you want to ask is, can my problem be solved with machine learning? In order for you to answer that, you have to ask yourself, do I have enough data to provide examples so that that thing can learn the concept? If you don't, exit. You've got no business being there. Until you can get the data, you're wasting your time. Second, you're like, OK, we've solved that problem. Now, what kind of machine learning do I want to do? There are various types. And we'll talk about this later. But at a very high level, how many of you have heard these terms, supervised learning, unsupervised learning, reinforcement, right? Various types. So you want to ask yourself, which one of these things is right for me? Will my problem be solved with existing ML? Remember, I'm a developer. I don't know machine learning. Has someone already done the work for me? Will it fit into one of these? If you actually zoom in, you can zoom in here, but if you look at it later, you'll see that at the edges, each one of these types gives you examples of the kinds of applications. So look at it and say, is my app like this? So then, if that's the case, then I need this type of machine learning, this type of algorithm, right? Say you even get past this part. You still have the third question. Should my problem be solved with ML? And at this point, you're talking trade-offs, right? You're like, is there even a benefit? Am I doing this just so I can put it on my resume and say I'm a machine learning expert, or am I actually getting something out of it, right? And the 3 things, the 3 kinds of benefits machine learning usually gives you is automation, performance, and creativity. For those of you with managers, you can add them as the 4th. You just do it because they tell you. That's OK, too. But in the bigger scheme of things, these are the 3, right? Automation says machine learning is going to save me cost and resources because it automates things that currently I'm dedicating human resources to, right? Those are perhaps the easiest problems for machine learning to take on. Second is performance. Machines can be less error prone. Machines can be faster. They can scale more. That might be the reason why. Third, creativity. Creativity is a new one, but it's really saying that there are certain cases where there's so much data that you as a human will never see the patterns to make the connections to take that and apply it somewhere, but a machine can. So if it can do that, then you really should be focused on that. I told you I'd talk too much. All right. So should my problem be solved with ML? And this is kind of like real examples of problems solved with ML. Excuse me. So at a very high level, look and see if your problem fits into one of these buckets, right? Image classification, just to know what's in an image. Fraud detection. Am I looking for anomalies in behavior? Weather forecasting. Am I trying to predict a value that's on a continuum? Recommenders and targeting, marketing, right? Am I trying to cluster people into a group so I can target them for a message? Strategic actions. Am I building a game where I need to know in real time how to strategize, right? Big data understanding. Have a huge volumes of data that I need to make sense of. I don't even know where to start. So once you figure out what bucket you're in, you'll be in better shape. Now you can get to step 2. You've gone past the scope barrier. You're like, yep, it's worthwhile me doing machine learning. Where do I start? Now you come to leverage. Has someone solved my problem? Can I reuse their learning? So if you think that there is a machine that has been taught these concepts that's sitting somewhere, right? This is the equivalent of saying, can I go to the machine learning Home Depot and rent out that thing, right? That's what you're saying. Why do I have to build it when someone already built it? In order for that to be true, they should be addressing the same problem, and they should have been working with similar data. Turns out there's a solution for that. That's cloud machine learning. Everyone is in it. So Google Cloud has an offering, Microsoft Azure, Amazon Machine Learning, IBM Watson. Clarify, because I have to give a shout out to New York City. They're a startup. They're super good. They're like custom modeling, which is kind of unique. And I believe Facebook is also getting into this, right? So here, your thing is, I can get a machine that is already taught these concepts. It sits in the cloud. It can scale. And it's interactive. I can ask it something, and it tells me in real time. Why would I not do that? So the downside is that when you do this, that cloud has to match what you want. So here are the kinds of products, and this is an example of Google Cloud, right? Here are the kinds of products that exist in Google Cloud where effectively what you're saying is there is a machine sitting behind this API that I can ask this question and it'll give me an answer, and I didn't have to know anything other than how to use an API. How many of you here know how to use an API? That's what we are. Like, developers know how to code to APIs and libraries and methods, right? So let's break this down and see what kinds of stuff are available in the cloud. At a very high level, everyone wants image analysis, so that's the Cloud Vision API. Cloud Vision is basically saying, give me an image and I'll tell you what's in it. And remember, I said that you have to go to a cloud machine that can solve the problem, which is, hey, I need to know what's in this picture, but that actually has been working on the kind of data that you have. So if you're saying, I want to see what's in pictures, sure, that'll work. And we're going to talk about another case later. So this image analysis just says, here are all the things in this picture. Text analysis. It's like, hey, I'm going to give you some text. You analyze it and tell me, what is the sentiment? Is he happy or sad or angry? Like, this could be the kind of thing where people are posting comments about your product. Hey, you don't want to pay a guy to sit there and read comments and answer. You want to write a machine that says, read it, and if he's angry, respond immediately and say, I'm sorry, maybe trigger coupons, who knows, right? That's what you kind of do. What does text analysis do? It gives you sentiment. It gives you entity recognition. We'll look into that a little bit later. But it really is looking at written text. Speech recognition takes that one step further. It says, hey, people don't write stuff, they talk. How do I then take what that audio stuff is and convert it into text, and then I can reason on it with other stuff? And then building on top of that is language translation. What if they're talking a language I don't know? Can machine learning translate for me and then convert from speech to text, then go to text analysis? You see, you can start building these stacks. And finally, video analysis was their latest offering. And video analysis takes it beyond image. Because with image, you've got one fixed size content, right? Video is a sequence of frames. So with video intelligence, you're like saying, what's in the entire video on all the frames? Plus, I want shot detection. When did it change? Am I OK?
I don't know, say something.
OK. Oh, OK. Let's just keep it there, and I won't move. I can do this. Video analysis, right? So here you want to be able to say shot detection. When did the shot frame change? What happened? How many frames is this object in? Things like that are super, super useful to us, given how crazy people are about uploading video these days. So the thing in all of this that I want you to look at is that here, this plays to our strengths. We have an API. You make a call, you get a result. You didn't need to know machine learning, but you used it. And here, I'm kind of going to walk through, I think, just 3 of the APIs. Cloud Vision. So in Cloud Vision, you can do things like, thank you. In Cloud Vision, you can do things like detect faces. If there's a face, and for privacy reasons, they don't try to do face recognition. They don't try to tell you who the ID is. They just say, there is a face in this picture. You can get bounding boxes that tell you where the eyes are, the nose is, whether they're wearing a hat. All of this stuff simply by uploading a picture. Labeling. You can just post a picture, and it'll tell you, are there bridges in here? Are there roads in here? What kinds are there? Ships and trucks and cars in here, right? OCR. I can post a printed version, a picture of text. It'll actually extract the text out, give me the string, and then I can do other stuff with it. Logos. Logos are interesting because even if they're occluded, meaning if they're hidden, if they're warped, it can try to make a much educated guess on that. That works, especially if you're doing things like advertising. Safe search, it can tell you if there's like nudity, violence, any kinds of things that you flag for like, say, children. Landmarks, it can tell you, does this photo have a well-known building or a natural landmark, right? So all of this you get for free. How do you do it? Super simple. You go to the endpoint for each of these services. You say, here is my image endpoint, and here is the product I want you to look at, like logos. It says, OK, great, here's your JSON file back, which has all the logos that I could find in there. And here are the locations, the coordinates where those are found. Done. You didn't have to know what machine learning was, but you could get to that major use case, right? I won't go into all of these simply to save myself time, but natural language is useful when you want to extract entities from text, like nouns, cities, people, and sentiment analysis. Is he happy? Is he sad? Based on what's being said. Speech works on audio. It works on both streaming audio and stored audio. And you can think of it as first converting that audio into text and then being able to give you something that you can work on. Again, you can do things like content filtering, make sure that there's nothing offensive, et cetera. And then, now it gets interesting. So I've been talking cloud. You're a developer. I told you, hey, API, you don't need to know machine learning. You're like, that's great, but I'm a mobile developer. And my phone is not always connected. We got to be offline first. How do I do this now? This is where there are mobile versions of these APIs as well. And slight difference. When I say mobile vision, the interesting thing is mobile vision isn't just a kind of like a thin library that talks to the cloud. No, it literally has the trained model on your phone. So in that sense, you're going to get all the benefits of some of these APIs, not all, but they live on your phone, so they'll work wherever you are, even if you're offline. Here, face API, again, face detection. Barcodes. You can actually, in real time, hold up your phone to a barcode, and it'll tell you what the barcode has. Text. How do you use it? This is a very simple, and some of these slides have been taken from a standard deck. But here, you can kind of see really, really how simple the code is, right? You create a detector object, which is a standard class, instantiate it, set the kind of data. You say, what kinds of landmarks? Do I just want to know the faces? Do I want to know the eyes? What do I need? And then you build it. And once you've got it, you've got that model. You've got an object that you can ask questions of. Then you say, I'm going to ask you a question by asking you to detect those landmarks in this image that I give you. And when you give me that image, it returns to me back a kind of an array of landmarks. And then I can just walk through all those landmarks, and those landmarks are going to tell me, here's where the eyes are, here's where things are. And after that, it's fairly simple to say, OK, I'm going to go to the eyes and replace it or overlay another image on top of that, right? So it's an easy-to-use Java API because it's currently there for Android. I don't remember. I think it's there for iOS as well. I'm not an iOS person. But it's really that simple. And again, plays to your strengths as a developer. You're just using the API, right? This is the text analysis one. Live barcode detection, you can see in real time. And then you can do interesting things like combine vision and translation, right? So you can actually have something in real time detect that the image has text, take that text, send it to the translate API, get it to translate into another language, bring that back and overlay it in real time. So you can go around as a tourist and still be able to read all the signs. If you've ever been to Japan, this is super helpful. So at that point, you are at a stage where you're like, OK, I'm a developer. I knew APIs. I needed an example. Somebody had already trained a machine. I just used it. But what happens if that model, that the trained machine, was not exactly what you wanted? Can you retrain their models to get better accuracy or customize them in some way, right? So we're going to talk about that as the adapt stage. So the problem is, till now, you were just dealing with APIs, right? You didn't have to know anything about what was happening under the hood. Now, you're like, hey, I need to actually adapt the stuff. I need to look below. I think I lost track of my time. Oh, well. Oh, we'll see. So now, if I run out, I'm sure someone will tell me. So now we're going to do a machine learning 101. How many of you here have worked with machine learning before? Awesome. How many of you are data scientists? You've actually done modeling? Like, oh, OK. So if you have detailed questions, those are the folks you need to go ping. No, I'm kidding. But for the rest of you, let's kind of do a very high-level 101 of what machine learning is. So go back to where I was telling you about the concept of parenting, right? So really, it's very simple. It's not very simple, but we should think of it as very simple. You need to have data. Whatever your examples are, first thing, do you have examples? Take those examples, and you're going to break them up into two boxes. One is the examples that you're actually going to give to the machine for it to understand the concept. The other is the test data that you're going to hide behind your back. so that you can actually test to see whether it learned the right thing, exactly the way you do with your kids, right? You learn this, and I'm going to test you on that. And in here, the model, which you see here, is basically the artifact that's the learned machine, right? What does that mean? It means it's inside that is really, at its core, an algorithm or some kind of learning function, which is trying to best fit or represent the data that you gave it. So in other words, if your data, if the examples that you gave were like saying, hey, here is all the attributes of this object, and here are the labels, your function should be able to fit this in such a way that next time you give it a new piece of data which has attributes, it should be able to predict the label, right? So that's your model. The training of it is really where you go to that function and say, hey, you start off as a function that's a generic one. I'm going to tweak all the constants and the parameters until I get it to be as close or as best or as accurate for my data as possible, at which point you have a trained function. The problem is that trained function is only as good as your data. We'll talk about that a little bit later, but that means that you've got to be responsible for how you get your data. Once you've trained it, though, that's when you've got yourself a model that you can ask questions of. All you do is you give it new data, and you say, now, for this new data, please predict me what the output should be. That's your prediction. And if your prediction is right or wrong, you can feed it back and say, OK, I need to do something else. But if there's one kind of like under the hood thing you take away, it's like machine learning has a very simple data flow. So 7 steps, but broken down in kind of boxes. First, you've got to gather and prepare your data. And gathering and preparing your data means collecting a representative sample, cleaning it up so that it's available for your machine, and then being able to separate it out into testing and training sets. Second, you've got to visualize and analyze the data. Because here is the thing, it kind of also feeds into the next step, but you've got this humongous amount of data that you've generated. You need to figure out, wait, which function should I start from? Does this data even look, and we'll see an example in just a minute, does this data even look like it lends itself to an existing learning function? I don't know. So visualizing it gives you an immediate gut sense of all these various things that matter, which one of these should I pick? After that comes the hard part. You've got to select your learning algorithm. Which algorithm are you going to start from as a way to see whether you can train your data? Once you've got that, you feed it your data, you train it. You kind of say, OK, let's try to figure out what the parameters of this function are that fit my data. Then you test it. And when you test it, you can go back and repeat this over and over again until the accuracy of your models is really high or reasonable. And then you're like, OK, I'm going to use a model, start doing stuff, right? The important part in this is selecting the algorithm. That's your make or break, right? Pick the wrong algorithm, and all the resources in the world aren't going to get you where you want to go. Selecting the model is key. So there's tons of learning models, tons of ways to slice and dice this. So I kind of try to simplify it. And this is actually taken from someone else's talk, and I can't remember. But I like the way it keeps it really abstract, right? Supervised learning is if you have a task-driven job. What that means is you know all the data. You know the labels. You have labeled data. And so you literally have a goal. You're like, I have a goal for you to do X. I can tell you what X is, and I can tell you the attributes. In that case, then you're going to go supervised learning. And ideally, you fall into one of 2 buckets, right? Classification or regression. Classification is if your data falls on discrete levels, right? It's categories. Whereas regression is if it falls on a continuum, prices, population, things like that. However, if you are learning on just data, someone's thrown a bucket full of data at you, and you have no idea what the attributes are, you don't know what's really happening, it's not labeled, but you're trying to make sense of it, then you look at unsupervised learning. You ask it, hey, can you see any patterns in this data? And at that point, you're looking at various things. If it's discrete, you look at association analysis and algorithm. Clustering, if it's continuous, can I just group this data into things that look like each other? And so on. Reinforcement is like the coolest thing, but also probably the last thing you learn. Reinforcement is where it's reward-driven. And it's really, really appropriate for real time where you didn't necessarily have data to have trained it before. So you're literally saying, hey, on the fly, you got to figure out and learn what the best strategy is to reach the goal. And those are usually agent systems where the way you decide whether your approach is right is whether you reach the reward or not. And each time you back propagate and say, OK, now I need to try again. So at a very high level, those would be the ways you'd say, which route do I want to go? And once you've done that, go back to your thing and you start your coding, right? And here is the good thing. If you are working with machine learning, there's a ton of good tools, and Python is your friend. So this is kind of like mapping each of these boxes to a bunch of Python packages or libraries that you can use to get started. So you're not really like starting from scratch. And specifically, we're going to look at scikit-learn and how we can do a very simple example with scikit-learn. So scikit-learn is one of a number of packages, but it's really, really Python's go-to for machine learning, right? It kind of gives you a whole bunch of routines and algorithms pre-trained that you can use. So how many of you know about the iris data set? Oh my goodness, OK. So like with every other technology on the planet, there's always a bunch of go-tos for like teaching you stuff, right? The iris data set is the most famous one for teaching you classification. So we're going to try to use this just to walk through the code and process for machine learning for a very simple classification task. And the iris data set, it really is about whether you can answer the question, hey, which type of iris is this? There are 3 types, setosa, versicolor, and virginica. And you're saying, I have data for these flowers, and the data I have, I believe, is sepal length, petal width, and sepal width, right? I have all this data that I've collected, and I've classified them. I've labeled each one of those with these 3, right? So I have all this data. Now, if you bring me the dimensions of a new flower, just based on that data, can I tell you what it is? That's the iris data set, right? And the way it works, so this is a supervised learning classification problem. And this is literally mapping that onto code. And this is with scikit-learn. For those of you who have not, who are interested in the stuff and you want to learn, can't recommend this book enough. It's Intro to Machine Learning with Python by Andreas Mueller, who's one of the core contributors to scikit-learn. Based out of New York City, yes. Really, hands down, it's very recent, very up-to-date, worth looking at. But let's go through the code. So remember the 7 steps? First step is gather and prep data. So you'll see how easy it is in scikit-learn. So scikit-learn actually for these examples has the data, but if it didn't, you'd load your data from your own file. So first you're going to start by loading your data into a file. Then you're going to do import train test split. This is where you're saying, here's all the data I have. I need that broken into training and test sets based on some useful metric, right? Because you don't want all the data to be used in training and how you're going to test it. You don't want 50-50 because that means that you might be missing useful information. Also, it does little things like it randomizes before it splits for you so that you know if by chance your spreadsheet had all the data in a particular order, you're not like self-selecting only a minor representation of it. So with a simple call, you've got yourself training and test data sets. Then you want to visualize the data. You want to say, hey, I have this data. Is this a meaningful thing for machine learning? To do that, there's another Python library called pandas. And you can use that. And when you basically, pandas allows you to manipulate data much easier. Plus, it also kind of like allows you to use things like matplotlib to visualize it. So in here, what you're doing is you're using pandas to take the training and test data sets and visualize it. And what you get, I'm sorry it's not going to be too clear perhaps, but maybe just enough to make the point. When you visualize it, you're going to get a scatter plot like that. And if you look at it, can you see that there are 3 distinct colors for each of the types? And in many cases, you can see that those colors do seem to cluster together. So this kind of just visualizing the data, right, gives you this gut feeling like, wait, there is something in here that lets me separate them. I can see there is some kind of clustering mechanism that lets me separate these out so I can predict if something goes into one of these categories. So first thing you want to do by visualizing is say, can the different classes be identified? Yes, it looks like they can. Then the second is, what's a good learning function that I can start with that will model this? So in this case, we're going to use k-nearest neighbors. So that's a classifier. Again, now you've got a pre-trained classifier with scikit-learn. You import it. You basically, you kind of like take that pre-trained classifier, and you ask it to fit to your data. When you fit to your data, you're actually giving it the training data and saying, here is the examples. Now go ahead and customize the parameters of your function to produce as low of an error as possible for this. And when you do that, there is a method, or there's a function you can call called predict, that the train model, that KNN, which you've trained on your examples, you can now give it a piece of data and say, based on what you saw before, what do you think the label for this is? And you can use that to see whether your current training was actually good. Like the parameters it came up with on this iteration, were they good enough to give you a good accuracy? If not, because you predicted it, and when you predict it, you can look at the accuracy by calling another method called score, where you compare the label it predicted against the label you knew, because it came from the test data. say, hey, this is not accurate. I need to go back and do this again and again and again until the accuracy gets to a point where you're like, OK, this is acceptable. At that point, you can now start using that to predict labels for new information, right? So my point was not to tell you, hey, this is the best classifier. It really isn't. People and data scientists in the audience are all hitting their heads going, why is she talking about this? This is so bad. But it wasn't. My point was to tell you that as a developer, the steps are actually fairly easy. There's a lot of help for you in these libraries. And so it's really about you finding out the right calls to make in the order and then playing with them until you get to a point where you're comfortable with the process. Now that was for, I should keep an eye on the time. That was for superficial learning, like basic, like learner concept. What's deep learning? Deep learning is when you really want to find patterns in high dimensional data, right? So in this case, this is like, is this a cat or a dog? How does that work? So neural networks are kind of like the new hotness for deep learning. And I've tried to like explain this many different ways. It's very hard to process. At a very simple level, this is how your brain works. They'll all tell you that. But I'm going to try to use an analogy that some of you will love and some of you will hate. This is like the management structure in corporations, right? There's your boss, your boss's boss, your boss's boss, and finally the guy who makes the decision, right? So think of it that way, that neural network is multiple layers. The bottom layer is all the grunt workers. They're doing the jobs. But each of them knows only about their little piece of the pie. They only have enough insight to come up with data or outputs on this. But their managers know all the grunt workers. So like, OK, the three of you together, I'll take your inputs. I give each of you a certain importance based on how good you are. And then the bias is, hey, I'm better than all of you, and I have my own little extra sauce to add to it. Now I come up with the decision. I give it to my manager, and so on. Until you get to the final layer, and that final layer has to take a decision. It's like, I have got the highest abstracted amount of information. Based on this, I can think with some probability it's this or that, right? So that's the way I think about neural networks. And again, there are tools for us to do this. So since we're talking Google, there's TensorFlow. So TensorFlow, and there are other open source machine libraries too, but TensorFlow is important for two reasons. It's open source. It's, I think, the highest rated, highest starred GitHub repo on machine learning libraries right now. But it's also the thing that powers all those cloud ML things that we talked about, mobile vision, et cetera. So if you're really thinking, I'm using those APIs, and then I want to tune them, you really want to understand how that works behind the covers. It's meant for research and production. It's cross-platform friendly, meaning that you can run it on a phone, on a desktop, on tablets, et cetera. And it's licensed. I don't know if the license has changed. It's maybe a little old. And it's currently being used by Google for some very heavyweight products. It's used in Google Play Music to recommend music to you, in Google Photos to facilitate search, in Google Gmail to do smart replies. So it's really production friendly. And the way you want to think about deep learning, that if you want to kind of understand the same thing that we saw a bit of code, I want to see how difficult it is to do deep learning kind of tasks with TensorFlow. So MNIST is a data set. Just the way there's Iris, there's MNIST. MNIST is a handwriting recognition data set, which is yet another popular example. In this, you're given a huge data set of handwritten digits. And you got to figure out, based on a new handwritten digit, which one of those it is. So you try to train it on all the different ways people could write digits. Then you give it someone else's digit and say, can you tell me what this is? So deep learning is, this is what we see. That's what the computer sees. So the computer is actually seeing immense multidimensional data. It has to learn to make sense of that and say, that's actually a 1. How it learns. So if you want to take that same thing and apply it, like what are the steps? And I'm only showing this code to tell you it's the same kind of steps, right? And you'll also see that one of the things they did when they started TensorFlow is they really tried to make that API as close as possible to scikit-learn, so you would kind of have that familiarity. Same thing, you load a data set, you pick a classifier from their library. Once you've got a classifier, you fit the classifier to your data set. Then you check to see how accurate it is when you train it on your data. And if that accuracy is good enough, you can then have a custom fit classifier that you can use to predict stuff. I have 10 minutes, so I'm going to try to wrap up really quickly. I think I might actually be good. So right now we're like looking at, OK, I opened the hood, looked inside. I know how machine learning works. Here are the stages. Here are the APIs. Now I need to start working with them. This stage, you're really like, hey, I'm still using someone else's machine. I'm just training it on my data. But there may be a point in time where you're like, I actually need to like come up with my own new model, right? So an example I'll say is like, say, Google's data set for image is based on all the photos people have uploaded. But what if, and actually someone in New York did this, which I was super happy about, what if you decide to go back and pick every comic book in the world, scan them, cut them out, create images, and then train it to recognize Batman in the first issue, right? What does that mean? Do you really think that the models that are out there have all those characters in detail? Probably not. That's your custom data set. You may have a different way to do it. So in that case, you want to think about what it takes to build your own trained machine from scratch. And the only advice I'll give to you as a developer is that at that point, you really are getting into the nitty-gritty of data sciences. You better be prepared to brush up your linear algebra and your statistics. And most importantly, you better have a vivid imagination. Because the hardest thing I've learned in machine learning is there is no science there sometimes. It's like all art. It's guesswork, explore, trial, and error until you get to where you want to go. But one of the things that's important is you learn the ecosystem. Find out what are all the different types of machine learning, the algorithms that are there, so you have a gut sense and intuition for how they work. And once you do that, then you start working on, hey, I'm going to pick one of these to start from. And then the challenges are, how do I tune the parameters? How do I engineer features? How do I pick features from the data set that I have to make it most viable? How do I select the starting model? And so on. So in the last couple of minutes, I just want to address the last part. All of this was machine learning, pragmatic, what do we do? Great. Why, right? Why? Even if you didn't have a single job as a human being who's going to live in an AI world, why is it important to us? It's important because machine learning is seeing bias. So this was, to me, kind of like, lots of headlines like these are coming out. Machines are taught by photos to learn a sexist view of women, right? You may smile, but it's true. Because of the way the labels were, it was like, oh, if there's a woman, it must be a domestic job. If it's a guy, it's an industrial one, right? And this is not true. It's just that the data was not representative, right? But the problem that they found is a machine-learned software that's trained on this. It didn't just mirror it. It amplified it. So you may have said that was just an accident, was one thing. But that thing says that is the default. Now I know, right? It kind of amplifies its own understanding. That's dangerous. Second kind of bias. How many of you remember this scandal with the whitewashing? Snapchat had filters, right? And the intelligent algorithm said, hey, beautify, if you apply the beautify filter, I'm going to make your skin lighter. What does that tell you, right? Like, so there are these, it wasn't a bias, it was just an aberration, right? It was not done right. But the fact is that once the machine learned it, it just amplified. It's like, oh, they wanted light, let me go lighter, and then it was crazy. Bias is important, we need to avoid it. Second is the ethical question. Just recently, a company called Dopamine Labs had this, right? They were like, we want to make tech with AI that makes you even more addicted to your phone. Really? And this is Francois Cholet, who's one of the AI researchers. And he was like, saddest thing I read today, if you work in AI, you have de facto power over others. Remember to exercise that power responsibly. If your AI is getting people addicted to stuff, is that really for human value, or is it for something else? But you have that power. Right? And finally, there was this wonderful TED Talk that I saw that I really loved. And it said, we're building a dystopia just to make people click on ads. The whole advertising industry is driven by machine learning and AI, right? So they optimize behaviors to get you to click on ads to make money. But what they're really doing is building more data, because when they got you to click on ads, the machine thought that was realistic data, and it's amplifying that. And the problem with this is that if all of us, developers, designers, even if you never work in machine learning, if you don't have your voice heard, that data that the next generation of services is being trained on is not representative of you. So even if you don't care a hoot about it, you're going to get in there and look at the algorithms and try to play with the data and say, wait, this doesn't cover my use case. I need to retrain. And that's what I think is important. So recap. At a very high level, my goal today was really to talk about how you can navigate this kind of like complex area of machine learning in a way that makes sense if you're a developer. So rule number one is be pragmatic. First thing, know when you should exit. If this is not relevant, just exit right away. Don't waste your time. But if you're going to stick with a course, look to see if you can reuse models someone else has built for your problem, then work your way towards understanding how to retrain them. And only then, if you really think that that does not solve your problem, do you get to the point where you're like, I'm going to build my new models, at which point you really want to start getting into data sciences. And when you're done with all of that, regardless of which level you are in of the stack, keep in mind, be ethical, and be adversarial. Adversarial is actually a new thing, but it really means even if you don't work in machine learning or AI, you can be an adversary. You can go and challenge the AI to see whether its behavior lives up to your expectations or whether it's inadvertently doing things that are malicious, and flag them. The sooner we flag them, the sooner we combat them, the sooner we get the bias and ethical things out of our system. And I think that was about it. All of these are just like resources that I was using in the slides. All the links to things like CloudML, Mobile Vision. And finally, the slides are available at that bit link. I have to clean them up and put some attributions and stuff like that. I will post them to Twitter. Thank you all for listening. My takeaway message is I'm not a machine learning expert, but I've learned like in 20 years that pretty much everything I've worked in, I learned on the fly. And I think that's the way it's going to be. So I think we all need to participate in this ecosystem if we are to make it fair. Thank you.